Alright, so here we go. 0020. This is the beginning of your week 3 videos. Big focus on this unit is going to be on algebra. We're going to talk about lines or linear equations. We're going to talk about really the guts of algebraic expressions and manipulations and all the vocabulary associated with them. So this is some pretty important stuff. So solving linear equations is a very, very important topic. So you need to be able to solve things. It's very, very important to understand when we call something an equation, what we mean is that there is an equal sign, simply put. So now our goal to solve this, to solve for the unknown, to solve for x, is to isolate the variable or isolate the unknown. In this case, we want to isolate x. So we want to get x on its own side of the equal sign. All right, so what I'll choose to do is I will choose to, I'm going to bring my x's to the left. So if I subtract 2x from one side of the equation, it's like a scale or a balance beam or like a teeter-totter, whatever you want to call it. To keep things balanced, whatever you have to do on one side of the equation, you must do the exact same thing to the other. So if I subtract 2x from one, I must do it to the other. 2x minus 2x makes 0, so that's gone. So we just have a negative 6 over here now. And we can combine our like terms. I have 4x minus 2x. That's going to make 2x. And that plus 4 was still there from the original equation. So now we've started to bring our x's to the left. We're going to try and isolate them. So we're going to bring our numbers to the right. So I'll subtract 4 because, again, 4 minus 4 is 0, just like 2x plus negative 2x is 0. Those are known as like additive inverses. So now I only have 2x on the left. You owe me $6, you owe me 4, that means you owe me 10. Divide by 2, and x is negative 5. Also, when you're solving, like, x doesn't need to be on the left. So like if I had something like this, I could just as well subtract x from both sides. Those would just cancel out. X plus negative x makes 0. That's why we cross that out. They add to 0. 3x minus 2x is 2x. 3x minus x is 2x. Divide by 2, x is negative 2.5. So either way is fine. Your solving skills should be pretty awesome, and just know, it's a very important skill to have. So now, if you were to solve an inequality, you're going to do the same sort of operations as if you were solving an equation. Unless, and these are the kind of things that you should be adding to your notes, everything's going to be the same as if you were solving just an equation. However, if you multiply or divide by a negative number, you're going to actually like switch the way the inequality goes. So quick reminder, if I had negative x was less than 10, if I divide it by negative 1, I will have positive x here because the negative divided by a negative is a positive. I'll have a negative 10 over here. But just remember that that inequality symbol switches directions, so be careful whenever you, and they'll assess you on that, so be careful. Whenever you divide or multiply by a negative number in an inequality, you're going to switch or kind of flip the inequality, if you will. So let's solve one over here. If we have 2x minus 3 is less than 10x plus 1, let's go for it. So I'm going to bring my x's to the left, and I'm going to go kind of quick. Remember, you can pause me or rewatch this if you need to, or fast forward me if I'm not going fast enough. So I'll get my x's, I'll get them on one side, I'll bring my numbers to the other, and I'll divide by 8. And now remember, we're just pretending, the whole time I've done this quickly, but I've just thought of this inequality symbol, meaning this not equal symbol. I just thought of it, treated it like it was an equal sign, and just went solving away. I'll just have x over here, the greater than symbol, and negative a half. Notice, since I did not divide or multiply by a negative number, I do not flip the direction the inequality symbol goes. Similarly, you could, and I'll leave this as an exercise to you, if you want, you could bring your, you could subtract 10x, and then you'd have a negative 8x over here. You could add 3, you'll have negative 8x equals 4. And then if you divide by negative 8, be careful. The inequality symbol will switch, so you'll still have this exact same answer when it's all said and done. So that's going to, I would recommend that you do that just to experience the switching of the symbol, if you will, if you were to kind of solve this the other way. So that is important, and it's something to look for, because when you least expect it, it's going to happen. So I'm actually going to pause the video, and I'll just do that real quick for you. So now I'm just going to go the other way with this quite quickly, and I'm going to pause this, and all the work will happen quickly, up into a point. So right here in your solving, remember when we divide by negative 8 on both sides to keep everything balanced or equal, I will have x, I will have negative a half, however we must flip the direction of the inequality. And so either way I solved it, the original way that I had it or this way, you should get the same answer. And so just be mindful of that. Alright, so let's say you have a compound inequality like 4 is less than x, and x is less than 10. This would be written like so. You can just kind of push them together, if you will. So that means that x is between 4 and 10, but it does not include 4 and it does not include 10. So if you have a compound inequality, what you can do, like here's my little more complicated example, what you can do is you can break it up and solve each individually. You could say I have this left-handed inequality, I'll deal with that. I have this right-handed inequality, I'll deal with that, and then just kind of merge them together. So kind of get the left one, the right one, and merge them together, just like that example. Or I'm going to do this in one fell swoop. Just pretend that you're looking on the left-hand portion, and you'd say, oh, okay, I want to get x alone, I want to isolate x. So your gut should tell you you want to add 8. But so now what I'm going to do this all at once is I'm going to add 8 to every portion. So I've got 18, 3x is now isolated, and 30. Now, to get x isolated, we will divide by 3 on every piece. Again, we're trying to keep everything balanced here. So then we know that x is between 6 and 10, but it is not equal to 6, and it is not equal to 10. Okay, very good. So the associativity law says that it doesn't matter how we group numbers, i.e., which we calculate first. So, for instance, if I had like 1 plus 2 plus 3, it wouldn't matter if I grouped 1 and 2 together. You could say, oh, look at those parentheses first, 1 and 2 makes 3. Then you could add an additional 3 to it. It gets a 6. Similarly, I could associate or group together 2 and 3, get 5, add 1 to it, and then I would still have 6. So associativity works when we add or multiply. Same game, 3 times 5 times 4, or 3 times 5 times 4. Let's say I associated the 3 and the 5, or the 5 and the 4. In the first situation, I'd have 3 times 5 is 15 times 4 makes 60. In the second situation, I'd associate or group together the 5 times 4. That would make 20. Then I could times it by 3. I'll be at 60 as well. A lot of times my students ask me if I'm allowed to do that. So that's a very, very important idea. Commutativity says, the commutativity law or property says that it doesn't, we can swap numbers, kind of switch up their order, and we'll still get the same answer. So for instance, let's say I had 5 plus 7 plus 9. That's going to be the same thing as if I did 9 plus 5 plus 7. So I can kind of switch things around, and either way you cut it, either way you splice it, I'm going to have 21 in this situation and in this situation as well. Same thing goes for multiplication. So if I had, 5 times 7 times 2, that's the same as 2 times 7 times 5. no matter which way you slice it, you'll have 70 in this bottom example. And for this example right here, again, you will have 21. So it's just important to have confidence in using the appropriate language, and also having confidence that you're still doing things correctly if you use the associative or the commutativity properties. So a little interesting factoid. If you think about it, let's say we did commutativity. Let's say we did that with subtraction. Let's say I had 3 minus 4. Is that the same? That's a question mark equals. Is that the same as 4 minus 3? So in fact it's not. -1 is not equal to +1. So just be careful. This example, you might say, well, what is he getting at here? Well, if I had 3 plus -4, that would be the same as -4 plus 3. But notice how you have to take, that makes -1, that also makes -1. But in this situation up here, you can't just switch which term is negative and expect to get the same result. So just be careful on the difference here. So the distributive property is very, very important. If you had something like 4 times 2 plus x, or 5 times 7 minus 2x, both of these examples would be great situations for the distributive property. So what I mean by that is this 4 is being multiplied by this binomial here, this thing with 2 terms, like a bicycle has 2 wheels. Just like this 5 is being multiplied by this binomial over here, this thing with two separate terms. So 2 non-like terms separated by addition or subtraction. So in either of these situations, the distributive property says that what we can do is we can distribute our 4 to each of these terms, or distribute our 5 to each of these terms. So the distributive property is multiplication over addition or subtraction. So 4 times 2 is 8, plus 4 times x is 4x. Similarly, we'll have 35 minus 10x. So a lot of students tend to struggle with the distributive property, so it's a really, really important idea to have down. The distributive property is kind of like the opposite of factoring. And so now to really show the distributive property, let's say we have 2 binomials multiplied together. You have x plus 1 times by x minus 3, multiplied by x minus 3. Well, if you think about the distributive property in these 2 examples up here, we can apply this same idea. This x plus 1 is kind of like our 4. Our 4 was multiplied by each of these terms. Our x plus 1 will be multiplied by each of the terms in this binomial. So our x plus 1 will be multiplied by x, and our x plus 1 will be multiplied by -3. So you see, we're just repeating the distributive property here. Now it's kind of happening twice. So then we can distribute some more. This x is going to get distributed by both of these guys. This -3 is going to get distributed by both of these. X times x is x squared. X times 1 is x. We'll have a -3x here and a -3 when we distribute those. We can combine like terms. And so here's our final answer. If we were to multiply these 2 binomials together, here's what we would end up with. So this shows like the distributive property with 2 binomials. And notice, if we gave you something like this, you could factor or break it down. And if we gave you this to factor, your final answer would look like so. So the distributive property is kind of the opposite of factoring. It's kind of like multiplying out those factors to get a different representation of the same number. So the distributive property is quite important as well. So I'm gonna go at warp speed here. So in this situation, it's important to kind of use algebra to represent things in real life. So for instance, if we had a rope that's 9 feet long, we could divide it into two pieces. We could call one of the pieces x, and then the other, we could think of it as, so let's say we kind of divide it right there. The other portion, we could think of it as y. Then if you ask yourself, well, we could use y as that variable, but perhaps y could be in terms of x. So let's try that out. We know x plus y, let's say that's right where we cut this 9-foot rope, is equal to the total of 9 feet. Well, if we want, we could solve for y by isolating it. We could say y is the same thing as 9x. So actually, a better representation of this 9-foot rope would be if we cut it, let's say right here, this length would be x. This other length, instead of calling it y, we could call it 9 minus x. So there really is no need for y here. This is a good geometric and algebraic reason together. So situation or example together. So the other length we could call 9 minus x. So it's a good way to show how we could use algebra to perhaps break down a real-world problem and then perhaps go further with it. And this is also has some nice geometric context. So we've already talked about this a bit, but it's such an important skill that it's good to revisit. If we were to write a percentage as a decimal, if we had 79%, we could just say, well, percent means out of 100, so that's 79 out of 100. That's known as 79 hundredths. So a quick little shortcut, if you will, it's kind of like we could take this decimal place, which is right here, and we can move it two left. I think that's actually sort of makes it more confusing, though. Just remember that percent, like century, means out of 100. So we have 79 out of 100. That's 79 hundredths. Remember, that's the 10th place and the 100th place. If we had 130%, that's 130%, meaning out of 100. We would call that 1.3. 100%, that means 100 out of 100. That is known as 1. So if you take 100% of something, you're literally just taking all of it or 1 times it. So that's kind of a cool example as well. And let's say I had, like 4.2%. That's going to be 4.2 out of 100. That's the same as if we multiply the numerator and denominator by 10, that's the same as 42 out of 1,000 or 42 thousandths. Again, the quick and dirty way to do this is to take your decimal place and move it 2 to the left. But also it helps to think about decimals and kind of tie it all together. So I almost kind of want to shy away from that example or that shortcut. 30% of x, well, if we wanted 30% of x, well, we know 30% is 30 out of 100 or 3 out of 10. So that would be like saying 0.3 times x. Okay, so 30% is 30 out of 100 or 3 out of 10. 3 out of 10 is known as this decimal, 3/10, and then we'll times it by x. So it's a good algebraic representation of those words. Let's say we have to write an expression for 9% more than x. Well, if you think about it, more than x is going to be, that's going to be over or above 100%. So that's above 100. That's how much more than 100% of x? That's 9% more than what it already is. Because remember, 100% of something is exactly how much it is in its entirety. If we're going to go 9% more than that, we're going to be finding 109% of x. We would represent that as 1.09x. And last but not least on the slide, if we want to write something that's 12% less than x, well, we know that that's going to be below 100%. So how much less than its entire self, or it's 100%? That means it'll be 12% less than that. So that'll be 88% of its entirety, otherwise known as 0.88x. All right, so thinking above or below 100% is very, very important because, again, this crucial point that I didn't write it down, so I will now. 100% Well, that's 100. Percent means out of 100. That's the number known as 1. So that's like your important that's like your important dividing line, if you will. Because if you think about it, if you have this number x, it's really 1 times x. So if you have x, you have 100% of x. If you're going to have more than x, you're going to have more than 100% of x. If you're going to have less, a percentage less than x, you're going to have a little bit less than, let's say, the 100% or the 1 times x. So it's really an interesting, sort of like dividing line is the way I think of it. So I already did a video on this, so we'll be including that as well. So be sure to check this out. This is known as a mixing or a mixture problem, and these are kind of tough. So make sure you check this out because you want to get this right if they ask you this. And at your leisure, you can check out Deborah Borkovitz's website. It's really, really good. Check out the 0020 multiple choice questions. She has hints if you get it wrong and the correct answer, so it is quite nice. So just make sure you've got this stuff down, and good luck. Thank you.